So here we have a very interesting question which asks, is this a right-angled triangle? Well, right-angled triangles hopefully will make you think about Pythagoras. But if I look at the examiner's remarks here straight away, it says it's the most challenging question for all but the most able students. Indeed, the most successful students use Pythagoras, but those who try to use the cosine rule often made errors when trying to rearrange the formula. So using the cosine rule was something quite a lot of people tried to do. So we're going to think about that first and then bring it back to Pythagoras. Okay, so the cosine rule is when you have a situation like this. You've got an angle here, so we'll call it angle A, and the side opposite we'll call little a. So this will be little b, and this will be little c. The vertex are b and c. Now, when you've got all three sides here, but you want to find the angle, then the cosine rule is indeed what you think about. And the cosine rule is when you write cosine of that angle is equal to these two sides, the sum of the squares of these two sides, so b squared plus c squared, minus the square of the opposite side, so minus a squared, which is then divided by 2bc. So all over 2 times the product of b and c, so 2bc. Now, what will happen here when you start to think into this is, okay, what am I trying to do? I'm trying to prove that this is 90 degrees. If I try and prove that it's 90 degrees, if it's not 90 degrees, that's fine, but I'm trying to prove that it's 90 degrees so that I can then say, yes, it is a right-angled triangle. Well, the cosine of 90 degrees is 0. So using this formula then would give me then, next step would give me b squared plus c squared minus a squared all over 2bc equals 0. So if I multiply both sides by 2bc, that will actually remove this denominator. Okay, so that would cancel. 0 times 2bc would just be 0. So that would cancel the denominator. And I think you can probably see what's happening now. If I rearrange this, so if I put the a squared over onto the other side and change the sign, I'll end up with a squared being equal to b squared plus c squared in a right-angled triangle. So that's simply stating Pythagoras, the Pythagorean theorem. Pythagoras says, indeed, that a squared equals b squared plus c squared. And it shouldn't surprise us because we derive the cosine formula from working with Pythagoras and what we know about cosines. So it's not a great surprise that it reduces back to the Pythagorean theorem, but I suppose it would have saved time if you'd realised that you could just straight away work with the Pythagoras formula, so a squared equals b squared plus c squared. So that's what we've got here. Here's the hypotenuse then, which is the square on the hypotenuse equals the sum of the square of the two sides. So this is a squared, that's the hypotenuse, and these are the two legs of the Pythagorean theorem. Okay, so that's the cosine law and how that works dealt with. All boils down to the Pythagorean theorem. So let's now do what's necessary to sort out this triangle in terms of Pythagoras. Well, that means finding the squares on each of the sides. So what we're going to do now is square these lengths here, and in other words we'll have to square 5.8 times 10 to the 2, or 10 squared, 1.16 times 10 cubed, we'll have to square that, and 580 root 5. So here we've got a surdic length, so a surdic quantity. Now, one thing I can see straight away is that 5.8 and 580 are related. And in fact, if I think of, well, if I, for example, multiply this by 10, so just rearrange this in a way. Multiply this by 10, so I've got 11.6 times 10 squared. Okay, then 11.6 is also a multiple of 5.8, so I've got 5.8 times 2 times 10 squared, in other words times 200. I'll just write it out as 200. And this one here is 5.8 times 100. And here we've got 5.8 times 100 as well, but times root 5, so 100 root 5. So it's a good idea to make these consistent, because then what we'll be able to do is, well, it will just save time, save calculation, and mean we can work through it more effectively and with less error, I hope. Okay. So you don't have to do that. You could just work with the calculator, but I think the numbers are going to get pretty horrible if you do. What I'm going to do now is square all of these sides. So I'm going to start with this one. So let's have a look at b squared. Now, what it means if I've got the expression like this is I can square this and square this. This is very easy to square, so all I really need to worry about is this one here. And if I do this on my calculator, that comes out at 33.64. So 33.64 times 10,000. Now, to avoid the zeros, I'm just going to put 10 to the 4. But you see, when I come over here, if I now write c squared, then I can use the same calculation. So I've also got 5.8, so 33.64 is 5.8 squared, and 200 is easy to square, so that's going to be 4,000. So it's going to be times 4, again, times 10 to the 4. Prevents me getting lost in the zeros. Okay, well, that means I just double it and double it again. That's going to be about 125, about 135. So let's look at it on the calculator, and there we go. It's 134.56, in fact, times 10 to the 4. Okay. And times 10 to the 4, I'm going to try and make that consistent as well. But let's see what happens here. If I square this, so I've got a squared. Again, it's 5.8 squared is 33.64 times, well, 100 squared is 10,000 again, so there's my 10 to the 4. But it's going to be root 5 squared is going to be 5. So root 5 times 10 to the 4. Now you don't have to do it this way, like I say, but being quite, being quite fluent with numbers, understanding how to work with surds, standard form, that sort of thing, you can see is very helpful in this kind of question. Speeds us up and avoids error. Okay, now 33.64 times 5 is the same as 33.64 times 10 divided by 2. Is an interesting way of thinking about it. So what have I got? Where's my calculator? There we go. I've now got 168.2. Which again, if I think of that, 35, yeah, 5 times that is going to be around 168, so that's good. Okay, so there we go. So quite laborious, but what we've done now is we've squared all of our sides, exactly as we are asked to do in Pythagoras. So we have to square each of the sides, the square on the hypotenuse, should equal the sum of the squares on the other two sides. Well, let's see if it does, because if it does, then we've proved that it is definitely a right-angled triangle. Okay, so we've got a squared. We now need to add b squared and c squared. So let's write it here. B squared plus c squared equals, and I can distribute the 10 to the 4 now, so I just need to add the b squared, the first term here, so 33.64 plus 134.56 times all of that times 10 to the 4. And if I check that on my calculator, it looks like it's going to work out. Yes, it does. So that comes out as 168.2 times 10 to the 4. So I've got a match. Okay. So I've got a squared equals, so I can write a squared equals b squared plus c squared, which means it must be a right-angled triangle. And I'm just going to put in brackets by Pythagoras. So, don't need the cosine law. You do need to understand your Pythagoras. And with questions like this, you need to be really careful how you calculate these things and make sure you avoid error. But if you get it right, it works out very nicely. And we've proved, therefore, that this is a right-angled triangle.